So, today, going to start by explaining the difference between a time series model and a linear regression model. A simple one for now. Of course, there is the concept of a multiple linear regression model, but that's beyond the scope of this class. We're going to focus on a time series model. First, we've got to know what the time series is. A time series is pretty much a random process that is observed over time. We are in Florida, so we all know about spaghetti models, right? So the spaghetti models, they make predictions as to where things go. Time series plays a good role in meteorology, but you have some information as to where it started, where the hurricane started, or the initial depression, and how it moved over time. So, for instance, for the past 7 or 8 days, they tracked it, and we are at the 9th day, and we want a 3-day forecast, a 5-day forecast, and that's how they predict, based on what they observed over time. So, time series model pretty much is any series that you observe with respect to time.
Which, if you just look at hurricanes, you realize it's not always accurate, regardless of how much information you have.
That's true. The same with earthquakes. People are still trying to model, predict, where earthquakes would happen. Someday, maybe someday. I should take my time to do that. So Alex just pointed out, well, there is some, we can't predict the path of a hurricane accurately. Sometimes we get lucky, but still there is variation that is involved. So just like a linear regression model, which has noise involved, a time series model also has noise. So did I use AX plus B last time?
Yeah.
We'll stick with that notation. I don't want to confuse you guys. Epsilon and that is the noise that gets added, and that is what's going to cause variation in our data. Even though we're trying to fit a line, there is variation. We look for the line of best fit. We're not finding the exact line, but we're finding the line of best fit. So that's the underlying process, or the underlying pattern. If life were to be perfect, if there is no variation at all, this went away. This is purely deterministic. Do you agree? The line y equals 2x plus 1, it's deterministic. If you draw a line, it's a line. But what makes it random, it's that noise line. The moment noise gets added, things become random. That makes it fun. And the interesting part about noise, or an assumption that we make, that epsilon
You mean it's like a normal distribution, right?
Yes. Epsilon is distributed normally. In other words, normal distribution, what does it look like? It's a bell curve, right? A bell curve is symmetric. All it is saying is if noise gets added from this side, pretty much the same amount is getting added from that side also. We're not adding too much noise in one direction. We add noise in a very balanced way. In a shorthand notation, I'm sure the book probably uses it. I'm not sure, but it's very likely. Epsilon, squiggly, simply means distributed as. N stands for normal, means 0, varies sigma squared. It's just a shorthand notation to say that epsilon is normally distributed with mean 0 and varies sigma squared. Good. I know this thing.
We can always just turn our desk that way and use that way for
This way. Epsilon is IID. IID stands for independent and identically distributed. That simply means every observation So each observation in your sample is independent of every other sample, every other observation that you have in your sample or data. So that's what we mean independent. Identically distributed simply means that if the first observation has a noise that satisfies that condition, every single observation in your sample must come from that distribution. Does that make sense? Identically distributed. That is a general form of writing it, but for the ith observation, that's how we subscript it, and we'd say that's the model for the ith observation. If you recall from last time, the value of n happened to be 5, I believe. I wrote 5 numbers for x, 5 numbers for y. So we pretty much had x1, y1, x2, y2, x3, y3, all the way up to x5, y5. All I'm saying here is if I pick one of them, the ith observation, it has to have the same type of noise. When I say the same type of noise, I'm not saying the same value I'm not saying 5 gets added. Rather, I'm going to say it comes from that distribution. So pick a number from these two values. Oops. Minus 3 and plus 2.
So like -2 and 1 would be in the same distribution?
Yes. So possible examples for epsilon. So -2, -1. What's that? Just a few more examples. 1, 2, right? So in a balanced sense, but this is just an example. But if I change this graph, and if it is no longer normally distributed, rather, if it had something like that, most of the noise will get added from what interval? 1. Exactly 1 or 0 to 1. Think of it like a bar graph. Where does the majority lie? Between 0 and 1. The bulk of the values lie there. And if you take possible values for epsilon I, as an example, could be 0.5, 0.22, 0.4, 0.7. Maybe one of them would exceed 1 and you get 1.2. So the majority of values that you get would be between 0 and 1. Do you have a question?
Yeah, how is the noise represented by that? Is that a normal distribution?
I'm about to address that. So, of the two, yes.
How far would you say that possible epsilon I values could go past 1 before it starts getting unreliable?
It just depends on the sample. If it follows this distribution, there is a good chance that the majority would lie between 0 and 1, and a tiny percent would lie outside the boundary. So, this is a bulkhead, right? This is not a bulkhead. When it comes to linear regression, this is okay. This is not okay. Does that make sense? This is perfectly fine. This is what we want. That is our assumption. And it can't be skewed in that sense. Does that answer that question? Now, every observation is independent of every other observation. Simply means the -2 that got added should not have an effect on that -1 that gets added, and so forth. Now, moving on to a time series. And let's go with the hurricane example. Let's say, we've all seen that NHC picture, right? They put crosses. Let's say the cross appeared close to Central Africa. Okay? And it sort of kept going in that trajectory. Do you think all of a sudden it's going to jump up to, close to Camden? No. Nature doesn't work that way.
Also, when did it have to cross the equator?
So that's beyond the scope of this. So we're talking about math, not meteorology. So we have, it kind of goes along, and the next position is going to depend on the previous 4 positions, right? It's not going to go too far, but it's going to be in that neighborhood. So how do we denote this? Just like the observation, at time t, we measure the value of y. That is going to depend on some time t, for some value of x at time t, plus the noise that got added at time t. Does that make sense? Now, again, what causes variation in a linear regression model? Noise. This is the part that is causing variation. If we look at a hurricane case, if we did not know that at all, we can predict where the hurricane is going to go. Yes, if it started in Central Africa, straight line, somewhere it's going to go up there. But this is what's going to cause variation. Now, we sort of make the same assumption that epsilon t can I erase this? Let's consider the hurricane case. So, bunch of positions. It's going that way, and I sort of put that, and let's say that's the corner variation, right? So that's where the position is going to be. So what we simply mean is that this particular path is going to vary between those two values. So that variation is determined by sigma squared. So that's what I meant by saying, well, if I have a position here, tomorrow it's not simply going to jump close to Greenland or Antarctica, right? It's not going to happen. And if you look at it, there is symmetry. If you look at the graph that they show, the cone of projection or cone of prediction, always symmetric for the most part. In other words, the noise is getting added in a symmetric way. So how do we get that symmetric noise when it's normal, right? Otherwise, it's going to move in one direction more than the other. Great. Do you see the similarities between those two? Makes sense. Now comes the big difference.
That hurricane sometimes act like it was Katrina, and you moved it, just Louisiana.
What?
Well, I think it was 2008 or something, and I don't remember if it was Katrina or Wilma or whatever one that just hit Louisiana twice. I'm fairly certain that was not the code of prediction in any way.
It happens. So, 5 observations. If I asked you, well, do you think the position that I measured for this particular path of hurricane at this time, is it dependent on what we with what position that we measured the previous time?
Yes.
Yes. Y3 is going to depend on
Y2.
Y2, but in a way, it also depends on Y1, right? If it's dependent on Y2, Y2 is dependent on Y1, so naturally yes. Y4 is going to depend on Y3. Y5 is going to depend on Y4, and so forth. So all of these variations that get added, whatever is getting added, it always depends on the previous value. And not just, all of them, even though it makes sense that this Y5 could depend on Y4, 3, 2, and 1. Let's say it got close to the United States. Would it depend on whatever that happened in Central Africa?
Very, very vague, not really.
Not really, right? It has taken the path all the way close to the United States. And whatever dependence is going to happen, it's going to depend right here, not way out here. Does that make sense? So, what we are saying here is that whatever variation that gets added is not independent of each other. Previously, it was independent. Now, the fancy word that we use is correlated. Correlated simply means co-related. This one related to that one. That is related to that, and so forth. Now, how do we make predictions? Which we will see later on, it's all forecasting. We forecast depending on how far back this Wi-Fi is going to depend. So if I know whatever value that I observe today is dependent only on the past 2 days, I could go all the way up to Y7 and say, well, if Y5 depended on the past 2 days, Y7 is would likely depend on Y6 and Y5. Do you agree? But anything past that would be a mistake, or it'll be very erratic. It's not a good prediction.
Is that why when you look at those charts that they put in, it was like the first bit of the chart, like all the lines are together, and they start just seemingly randomly go off, like every possible.
Right, so for up to 3 days, it's going to be okay, and past that point, it's all over the place. Are we clear differences between a linear regression model and a time series model? Any questions? Now, okay, so there's a deterministic part. It's simple, it's just a line. But we could have all kinds of patterns that is deterministic. In both cases, you could have a quadratic function, you could have a sine wave, you could have a combination of a sine and cosine wave, both here and there. So those are complicated versions. We will stick with simple cases. Good. Okay.